to show you how to use the Essential Rainwater Harvesting tool, and I'm going to do an example at the same time. The example that I'm going to show you is actually the same one that's in your book, chapter 3. Note, however, that in the book, I show people how to create their own spreadsheet, and we're going to go through this same example but using the tool. Once you've got a copy of the tool open, remember that the very first thing you want to do is head to File and then hit Save As. Always start from a blank version. Start at the Start tab and complete the project information page. Anything you input here will be copied over onto your summary page when you go to generate a report. Select a monthly time step. We'll be talking about using a daily time step later. And select metric or US customary units. The tool contains a preloaded rainfall dataset for all major US and Canadian cities. To use the preloaded data, simply select the country, state, the dataset location, and under Climate Data Source, select Use Essential ERWH Dataset. And of course, if you'd rather input your own data, you can select Use and Input My Own Data. Now you're ready to go on to the Part 1 tab. The first step in Part 1 is Step 1.1, Collect Data. And the great thing is that if you're using our tool at a monthly time step, the rainfall data is already input for you. You can have a closer look at all of the data sets available under the US rainfall data and the Canadian rainfall data tabs. Although not necessarily required for any subsequent calculations, it's a really good idea to collect some of the following supplementary data, such as temperature, snow if it's relevant, wind, and humidity. If you've exported data from the website of the appropriate government agency for your country, you might have a CSV file that looks a little bit like this one. If that's the case, you can copy and paste this information directly into the tool. Continuing on to Step 1.2. So they know they already want to install a metal roof. From Table 3.1, they pull an efficiency of 0.95. Arguably, they could have used 1.0 if they felt confident that they were going to do a good job installing their gutters and minimizing losses. They've already measured that their house is 20 meters by 10 meters, and they can calculate area directly in the input field. Based on those input fields, the tool automatically calculates the average supply, both the annual total and the month-by-month totals. Now, Step 1.3 and 1.4 are combined. Here, we calculate the total water demands for the home, including even the non-rainwater uses, as well as the indoor rainwater demand, or the amount of indoor water that we intend on supplying with rainwater. If the family had past utility bills and a good idea of what their actual volumes were, their actual historical volumes, they would use Method A and input an average monthly indoor demand volume and an anticipated indoor rainwater demand volume. Using actual historical demand volumes is most likely to give you the best or most accurate results from the model. If you don't have this historical data, or if you don't have an idea of what the volumes would be, the tool gives you the ability to use typical indoor water usage ratings and patterns from North American homes. Note that this Method B is considered to be very conservative. There's 3 sections to the Method B table. In the first section, you're using a drop-down menu to select the pre-programmed fixtures, and the table will automatically pull up the manufacturer's rating and the average usage patterns from Table 3.2. Now it's the manufacturer's rating multiplied by the usage pattern, which gives you your daily indoor water volume in liters per day per person. In the second section, You can still use the drop down and pull up any of the pre-programmed fixtures. This time, the table will automatically populate with the manufacturer's rating, but you can input your own usage pattern. So remembering that the usage patterns from Table 3.2 are typical of a North American home. And if you know already that you're going to use far less water than a typical North American home, this might be where you would use this feature. The third section of the table allows you to fully customize and input your fixtures, as well as fully input any manufacturer's rating and any usage pattern that might be relevant for your design. So going back to our example, the family is planning on installing the following fixtures: 2 dual flush toilets, high efficiency shower, high efficiency faucets, a high efficiency dishwasher, and a front loading high efficiency laundry machine, and they know the manufacturer's rating is 76 liters per load. On the far right hand side of the table, where it says supplied with rainwater Y/N, they simply select yes for those fixtures that they intend on supplying with rainwater. In this case, toilets and laundry. Next, they have to input the number of occupants, which is found when you scroll down below the table. There's 4 people who live in this home. Now the demands, both for total indoor water and rainwater, are all calculated in the cells below. The next step, step 1.5, is about your outdoor rainwater demands. Method A is where you would input a value directly for liters per month. You'd use this method if you had an actual measurement or if you had another methodology for estimating your outdoor rainwater demand. Only use method B if you're looking for a rough estimate. Note also that at this point in this model, we're only inputting one value for the month. It's in the next step where you'll have the ability to vary on a month-by-month basis. Our Vancouver family is going to use the rough estimate method. They plan to irrigate their 100 meter squared backyard garden with rainwater. Because the midsummer high is between 21 and 32 degrees C, and the average midsummer humidity is above 50%. From the climate descriptions, they can see that they would be classified as warm humid. They input their garden area of 100 meters squared, and the tool calculates an estimated minimum and an estimated maximum amount of irrigation. By selecting conservative under risk tolerance, they're going to be using the maximum estimated volume in subsequent calculations. In this green input cell, they have the ability, though, to say what percentage of their total irrigation will be supplied with rainwater. As they're hoping to irrigate 100% with rainwater, they leave the value as is. In step 1.6, we combine our indoor rainwater and our outdoor rainwater demand. The tool shows the annualized basis, combined rainwater demand right here, and as well provides the ability to vary your indoor and your outdoor demand on a month-by-month basis. So if you remember back in steps 1.3, 1.4, and 1.5, we were really only inputting a volume for a given month. With your indoor demand factor, you can increase the demand for a given month. So for instance, if in the holiday months you knew you were going to be away and wanted to reduce your demand by 20%, you do something like that, right? And you do the opposite if there was months where you knew for sure you had a higher indoor demand. And your outdoor demand, basically it says plant irrigate percentage. This is where you have the ability to say, well, there's no way I'm going to irrigate in that month. And you can also irrigate less than your maximum, right? 100% is assumed to be your maximum. The Vancouver family knows that they only intend on irrigating in June, July, August, and September. So they set all of these months to 0. The tool now shows you your combined monthly rainwater demand. Before moving on to the last step, 1.7, let's bring back up the step-by-step process diagram. We followed all of the steps in the order shown, and we are now at the decision diamond. Supply over demand greater than 1. If your ratio is below 1, you're trying to use more rainwater than you can actually harvest on an annualized basis. You need to go back and either reduce your rainwater demand, increase your supply, or do a combination of both. On page 45 of your textbook, there's a bunch of options and ways you can do that. Remember that the supply to demand ratio is about making sure your planned uses for rainwater are not more than your rainfall budget. This can often be a reality check. Water consumption rates in North America vastly outstrip the amount of rain that can be harvested from those same homes. And even if your ratio is above 1, this does not guarantee that you have a viable system. You'll still need to complete part 2 and part 3 of the feasibility stage. It's actually a good idea to aim for as high of a supply to demand ratio as reasonable at this point, and especially if you are in a climate with uneven rain distribution patterns, or if you are designing an off-grid system with no backup or where backup is expensive. Again, I'll say that the monthly time step assumption will underestimate supply in the spreadsheet model. And so if you're slightly below 1 and your design is constrained such that you can't reduce demand or increase supply, you may consider evaluating your supply to demand ratio on a daily basis. We're going to get into this in an upcoming lesson. Going back to our example, the Vancouver family have a supply to demand ratio of about 1.6, which means they can proceed to part 2.